Hello, welcome. This is lecture 6. In this part of the lecture, we're going to introduce the concept of convergence of a sequence. Let's begin our discussion with the concept of a neighborhood of a point. Let P be a real number and epsilon is some positive real number. Then the set of all real numbers whose distance from P is smaller than epsilon is called the epsilon neighborhood of the point P. This set is denoted by this symbol. This shows the epsilon neighborhood of the point P. Here, D is a metric. For the moment, we may consider it as the Euclidean metric on the set of real numbers. So if D is the absolute value map or the Euclidean metric, then the neighborhood of P or the epsilon neighborhood of P in R is the open interval centered at P with radius epsilon, as shown in the following figure. So the epsilon neighborhood of the point P in R is the set of all points larger than P minus epsilon and smaller than P plus epsilon. This is the open interval. For example, the one neighborhood of 3 is the open interval containing all real numbers from 2 up to 4. Convergent sequences. Recall that a sequence is a function f from the set of natural numbers to an arbitrary set A. For example, f of n equals n squared is a sequence. And we used this symbol to denote this sequence. A sequence in R is said to converge if there exists a point P in the set of real numbers such that for every epsilon, a positive real number, there exists a positive integer n such that P sub n belongs to the epsilon neighborhood of the point P for all index n larger or equal to n. Here, P sub n denotes the nth term of the sequence. In other words, the absolute value of p sub n minus p is smaller than epsilon for all index n greater or equal to n. Which is shown in the following figure. So this figure shows, suppose we have a point P such that for every epsilon, the neighborhood of P contains all the points or terms of the sequence whose indices are greater or equal to the n. As shown in the figure. If this is the case, we say the sequence of the terms p sub n converges to the number p, and write by using this symbol. We may read the limit of the p sub n as n approaches plus infinity equals p. Or we may also write this way. The terms of the sequence are approaching the number p as n is approaching plus infinity. If this is not true for any sequence, then we say the sequence diverges. Let's see an example. Let this be a sequence in R. So this sequence contains elements like 1, 1/2, 1/3, 1/4, and so on. Then the limit of 1 over n as n approaches infinity equal to 0. Since for every epsilon, a positive real number, by Archimedean property, there exists a natural number n such that n times epsilon is greater than 1. Or 1 over n is smaller than epsilon. Now, for all index n greater or equal to n, we have the absolute value of the nth term of this sequence minus the number p, which is 0 in our case. This can be written as 1 over n, and by applying this inequality, we get 1 over n would be smaller or equal to 1 over big N, which is smaller than epsilon. So we proved this inequality, p sub n minus some real number p would be smaller than epsilon if n is greater or equal to some integer n. In our case, p sub n is 1 over n. The number p is 0. We proved that for every epsilon, there exists some n such that if we pick the index small n greater or equal to the fixed integer n, then the absolute value of the nth term of the sequence minus the p, 0, would be smaller than epsilon. Let's try to see the geometric meaning of this problem. Let's try to plot the sequence 1 over n. So we see here the first term is plotted here, which is 1, 1. And the second term is plotted here, which is 2, 1 half. The third term is plotted here, which is 3, 1 third. Similarly, 4, 1 fourth, 5, 1 fifth, and so on. Now, we see that, let's take a point P, whose coordinates are 0, 0. Now let's take epsilon is equal to 0.2. Now you see that for this choice of epsilon, the terms after 6 and onwards are within the lines defined by the equations y equals 0.2 and y equals negative 0.2. In other words, if we project the terms of this sequence onto the y-axis, we see that except the first term, the second term, the third term, the fourth, and the fifth, all the other terms are within these two dotted lines defined by the equation y equals 0.2 and y equals negative 0.2. So for this choice of epsilon, there exists some integer, for example 6 and onwards, such that all the terms of this sequence are within the p plus epsilon and p minus epsilon. In our case, p is 0, epsilon is 0.2. We made this choice. We can change it whenever we want. And p minus epsilon. So all the points from the term 6 and onwards are within this bands. Now for a different choice of epsilon, for example, even smaller, if we take epsilon as 0.1, then we see that the 11th term and onwards, if we zoom it enough, the 11th term and onwards are falling within these two dotted lines defined by the equation y equals 0.1 and y equals negative 0.1. So if this is true, that for every epsilon there would exist some index such that all the terms onwards would be in between p plus epsilon and p minus epsilon. Then the number p is called the limit of this sequence. In this case, the limit of the sequence is 0, as the terms are getting closer and closer to 0. Let's have a look at another example. The sequence 1 minus negative 1 to the n in R diverges. We first observe that if we define the terms of this sequence as p sub n, then p sub n is equal to 2 if n is an odd positive integer, or p sub n equals 0 if n is an even positive integer. For example, p sub 1 equals 2. Similarly, p sub 2 equals 0. P sub 3 equals 2. P sub 4 equals 0. Let's try to plot first few terms of this sequence. As we calculated, p sub 1 is 2, p sub 2 is 0, p sub 3 is 2, p sub 4 is 0, and so on. We note that the distance between the terms p sub n and p sub n plus 1 equals 2. To show this, let's calculate the absolute value of p sub n minus p sub n plus 1. This gives the absolute value of this quantity, which can be written as the absolute value of negative 1 to the n minus negative 1 to the n plus 1. This term here can be written negative 1 to the n times negative 1. That negative 1 would make this symbol as plus. So we have two terms of negative 1 to the n, whose absolute value simplifies to positive 2. So we proved that the distance between every two consecutive terms is 2, as shown in the figure. Suppose, on the contrary, that the sequence converges to some point p. Then there would exist a positive integer n such that for every index small n greater or equal to big N, we must have this inequality true. This is our some choice of epsilon. But the triangle inequality gives the absolute value of p sub n minus p sub n plus 1 is smaller or up to equal to the absolute value of p sub n minus p plus the absolute value of p sub n plus 1 minus p. This inequality is obtained from the triangle inequality. But this quantity is smaller than 1 from here. Similarly, this inequality is also smaller than 1 from the same inequality. But the left-hand side we just calculated was equal to 2 here, which is smaller than 2. 2 is strictly smaller than 2, which is clearly not true. This contradiction proves that our hypothesis about the convergence of the sequence is wrong. Hence, the given sequence diverges.